Hi everyone, I'm Mrinmaya Sachan from TTIC and ETH Zurich, and I'm excited to tell you about my work on knowledge graph embedding compression. Recently, there has been a lot of interest in learning embeddings of knowledge graphs in continuous vector spaces. These approaches represent entities as learnable continuous vectors, and each relation is modeled as an operation in the same space, such as translation or projection. A major issue in current knowledge graph embedding approaches is that the number of embedding parameters grows linearly with the number of entities. This is challenging when we have millions or billions of entities in the knowledge graph, especially when there are a lot of sparse entities or relations. Moreover, there is bound to be a lot of redundancy in the knowledge graph representations, as many entities are actually similar to each other. Hence, in this work, we present an approach to learn discrete knowledge graph representations, drawing inspiration from previous works in discrete representation learning. Each entity in the knowledge graph is represented as a sequence of D codes, where each code can take values in 1 to k. The codes for each entity are learned in such a way that they capture the semantics and the relational structure of the knowledge graph. That is, the codes that are similar are actually indeed entities that are similar to each other. This coding scheme is much more compact than traditional knowledge graph embedding schemes. So here is how this works. We augment the typical knowledge graph representation learning approach with a model for learning discrete representations. The approach is closely inspired from previous work in discrete representations and is an autoencoder which learns a discretization function to map continuous representations to discrete codes, and a reverse-discretization function that maps the discrete codes back to the continuous representations. The discretization and the reverse-discretization functions are jointly learned end-to-end and can be trained for any knowledge graph embedding technique with simple modifications to the optimization of the original model. The goal of the discretization function is to map the continuous knowledge graph embedding vectors into KD codes. We model this function using nearest neighbor search, as in previous work. Given continuous representations as query vectors, we define a set of key vectors. In order to learn these d-dimensional discrete codes, we partition the query and the key vectors into a set of d partitions, where each partition corresponds to one of the d discrete codes. Then we have two alternatives that allow us to do this discretization, in particular vector quantization and the use of the tempering softmax. The goal of the reverse discretization function is to map discrete KD codes into continuous representations. We model this first using a very simple linear model, which maps the discrete codes to continuous vectors by simply looking up the learned codebook. Then we also have an alternative, a nonlinear model, which is based on LSTMs. We evaluated our approach on 4 standard link prediction datasets, 2 from Freebase and 2 from WordNet. We learned these discrete representations corresponding to a number of continuous knowledge graph representation learning methods and compare the obtained discrete representations with their continuous counterparts. We use the same hyperparameter settings as in the original knowledge graph embedding papers for a fair comparison. We use standard evaluation metrics previously used in the literature, such as the mean reciprocal rank. And we also report the compression efficiency of the discrete representation as this ratio of the storage required for continuous representations and the storage required for discrete representations. So in this plot, we report the link prediction performance and compare the performance on various continuous knowledge graph representation learning methods. We have 4 discrete representation learning counterparts for each method, which use vector quantization or the tempering softmax for the discretization function, or the codebook lookup and the nonlinear reconstruction for the reverse discretization function. We show that the corresponding compression ratios of the codebook lookup and the nonlinear reconstruction approaches as these labels on the top of these bar charts. We find that the discrete representations sustain only a minor loss in performance and sometimes can actually even be better while be able to obtain significant embedding compression. So for example, here we obtain compression ratios as high as 40 to 500x. We have similar results on other data sets and other kinds of analysis in the paper, so I encourage you to read it. Thank you.